acephysics.org. Math and Physics Tutoring with Dr. Hudis. We'll be discussing a few capacitor problems. These are standard problems that come up in physics classes when capacitors are being taught. They involve taking a capacitor, connecting it to a battery, manipulating the capacitor, and then analyzing what things have changed in the capacitor, the charge, the electric field, the voltage, so on and so forth, and then redoing the problem, compare the results for when the capacitor is connected to the battery and when the capacitor was disconnected from the battery. These problems are standard and they come up in most physics classes. To begin with, I'm going to read the first problem. A 20 microfarad parallel plate capacitor with circular plates is connected to a 12-volt battery. 1. Calculate the charge on each plate. 2. If the separation of the plates is doubled while still being connected to the battery, now calculate the charge on each plate. 3. If the radius of each capacitor plate is doubled while still being connected to the battery, what is the charge on each plate? Part 2 to the problem. Now imagine the capacitor is connected to the same battery, fully charged, and then disconnected. We're going to assume no charges are lost during the disconnect. 1. What is the voltage across the capacitor? 2. If the plate separation is doubled, what is the voltage between the plates? And finally, if the radius of the plates is doubled, what is the voltage between the plates? You may want to hit pause and try this problem on your own. Part 1 says calculate the charge on each plate. Here's a picture of the problem. There's a 12-volt battery. It's connected to a capacitor. The capacitor is 2 circular plates separated by some distance d. This is the positive plate and the negative plate. I spent all afternoon drawing this picture. I'm quite sure it's the most beautiful thing you've seen all day. The question is, how much charge is on this plate? The fundamental formula for capacitance, or for capacitors, is capacitance, C equals Q over V. This can be rearranged using math to say Q equals CV. We're given the capacitance is 20 microfarads. Recall micro is 10 to the negative 6. The voltage is 12 volts. That says that the charge on the capacitor is 240 microcoulombs. If you have a 240 microcoulombs on this plate and negative 240 microcoulombs on this plate, for this capacitor, you will get a voltage of 12 volts. Part 2 says, if the separation of the plates is doubled, what is the charge on each plate? So here's 2. This is a cross-sectional view looking from the side. So this is the distance between the plates, and now the distance is doubled. It's still connected to the battery. What is now the charge going to be? Recall that the capacitance for a parallel plate capacitor is epsilon naught A over D. A is the area of the plate and D is the distance between the two plates. As you can see, if D gets larger, the capacitance gets smaller. If you divide by a bigger number, the capacitance gets smaller. In this specific case, if D is doubled, the capacitance gets cut in half. We know the capacitance is 20 times 10 to the negative 6. Therefore, when D is doubled, the new capacitance is 10 times 10 to the negative 6. That's half of 20 times 10 to the negative 6. And therefore, if you double the distance, the charge is going to be 120 microcoulombs. It's going to be less charge. It's going to be half as much charge as was previously the case. Therefore, a smaller capacitor means less charge is separated for the same voltage. If the capacitance value is smaller, you separate less charge to get the same voltage. This is something to think about and to understand and to try to let marinate in your brain a little bit. Part 3, if the radius of each capacitor plate is doubled, what is the charge on each plate? So the area, so now each one of the plates, the radius is doubled. The area is going to get bigger. Area is pi r squared. That's the area of a circle. If the radius goes from r to 2r, the area is multiplied by a factor of 4. And because capacitance is epsilon naught A over D, the capacitance is multiplied by a factor of 4. Therefore, the new capacitance, when the area is doubled and you still have D as the distance, is 80 microfarads, because 20 times 4 is 80 microfarads, and therefore Q equals CV equals the new capacitance times the 12 volts from the battery is 960 microcoulombs. So when the capacitance gets bigger, you need more charge has to be separated to give the same voltage. A larger capacitance needs more charge separation to give 12 volts. A smaller capacitance needs less charge separation to give 12 volts. Now imagine the capacitor is connected to the same battery, fully charged and then disconnected. what is the voltage across the capacitor? So here you have the capacitor. It's the same capacitor as initially was the case. It's connected to a 12-volt battery, and then you disconnect it from the battery. So the capacitor is just sitting here. It's charged up. By the way, when a capacitor is charged up, if you were to touch this capacitor, you could get an electric shock, which could be very serious depending on the size of the capacitor. So whenever you're handling capacitors, you'd like to discharge them first. When the capacitor is disconnected from the battery, what is the voltage across the battery? What is the voltage across the capacitor? The voltage is 12 volts. The voltage hasn't changed. The same amount of charge is on the capacitor as was on the capacitor before it was disconnected. The charge can't go anywhere, and so the voltage is 12 volts. Part 2 says if the plate separation is doubled, it's still disconnected from the battery, what is the voltage between the plates? So now you have these two isolated plates, they're charged, and you just have to imagine that you double the distance. Somehow you double the distance and you don't discharge them. Now, what is the voltage between the plates? Voltage is Q over C. If D gets larger, we already saw that the capacitance gets smaller. Specifically in this case, D is doubled, so the capacitance is going to be half as much as it would be if D was not doubled, if D was just not changed. V equals Q over C. That's Q over the new capacitance is C over 2, and therefore the voltage is doubled because this math shows that now there's going to be 24 volts across the capacitor. Finally, for part 3, if the radius of the plates is doubled, what is the voltage between the plates? Voltage equals Q over C. If the radius is doubled, the capacitance is multiplied by 4. So voltage is Q over 4C. That's 1 over 4 times Q over your initial C. Q over C is the initial voltage. That's 12 volts. Therefore, if the radius were double or the area of the plates were multiplied by 4, the voltage would change from 12 volts to 3 volts. There's many ways to see this. One is because the electric field becomes smaller. The electric field for a single plate, not for a capacitor, which is 2, but for a single plate is sigma over 2 epsilon naught. If this sigma is charge per area. If the charge remains the same, the area gets bigger, sigma gets smaller, the E field gets smaller, and the voltage would then get smaller as well. This is another problem. This involves some similar ideas to the previous problem we discussed, but this is a conceptual problem. It doesn't have any cantankerous calculations. It just requires you to take your brain, put it in second gear, and plow right on through. Let me read the problem. A parallel plate capacitor is connected to a battery and charged. If the separation between the plates is doubled, 1. How does the electric field change? 2. How does the charge on the plates change? 3. How does the total energy of the system change? And finally, charged plates of the capacitor are attracted to each other. To move the plates apart requires work from an outside agent. Where does that energy go? Where is it stored? There's a battery, and it's connected to a parallel plate capacitor. There's a positive charge density on the top, a negative charge density on the bottom, and there's some distance separating these two plates. Now this distance is changed. Someone takes these two plates and makes the distance bigger, and then we're going to answer these questions. You may want to hit pause and see if you can answer these on your own. How does the electric field change? Both of these two capacitors have the same voltage because they're both connected to the same battery. I haven't drawn the battery in this picture, but they're both connected to the battery. They both have the same voltage. Recall, voltage is electric field times distance. If D2 is bigger than D1, then E2 must be smaller than E1 because E times D has to equal the same number, the same voltage. So the answer to problem 1 is when you separate the plates, the electric field becomes smaller because the voltage must be the same when they're connected to a battery. Recall, this is connected to a battery, so don't get that confused. If this was not connected to a battery, it may be different. Question 2, how does the charge on each plate change? Well, the electric field is proportional to the charge. Electric field equals sigma over epsilon naught. That's inside the capacitor. And therefore, if the electric field is smaller in the case 2, this is the case 1, this is the case 2, then sigma 2 is going to be smaller than sigma 1, and therefore Q2 is going to be smaller than Q1. So how does the charge on each plate change? The charge on each plate decreases. Question 3, how does the total energy of the system change? Energy is equal to 1/2 CV squared. That's the energy stored in a capacitor. The V is the same in both cases. The only difference is the capacitance value. And we know that capacitance is equal to epsilon naught A over D. So if D gets bigger, the capacitance becomes smaller. Therefore, C2 is less than C1 and U2 is less than U1. So there's less energy stored in the case when the plates are separated than when the plates are close together. Charged plates of the capacitor attract each other. To move the plates apart requires work from an outside agent. Where does the energy go? Where is it stored? In order to separate these two plates, something or someone has to pull them apart, and that requires work. Where does that work go? That work goes into charging the battery. There's going to be charge that comes off of this plate and go through the battery. And that charge goes, so the work that you do in separating those capacitor plates, you or whoever separates them, is stored in the battery, and it goes into charging your battery. Hopefully you're using a rechargeable battery when you do this. Otherwise, the battery would probably blow up.